Our next session presenter is Yufei Ding, who's an assistant professor in the Department of Computer Science at UC Santa Barbara. And Yufei is going to be discussing compiler and runtime support for AI acceleration. So with that, let me welcome Yufei for the next talk.
Hello everyone. So I think we had a series of great talks this morning. And thanks for Frank's advocate for software optimization. And actually, my talk is mostly at the software level, and my talk's topic is compiler and runtime support for exploring AI GPU acceleration. So a little bit about myself and also my lab and our research. And if you look at the research in our lab, you will find that there are two major topics, and one is machine learning and the other one is quantum computing. You may find that how these two topics can be combined together. I can tell you the reason is because of the end of Moore's law. And because of the end of Moore's law, we somehow need to explore new hardware accelerator for different kind of applications. We cannot solely rely on some general hardware accelerators. That is one trend. And I believe that is mostly the topics we have focused on this morning. And for myself, I'm exploring two other alternative approaches. And the first one is, for example, can we explore other computation paradigms, for example, quantum computing? In that way, we could somehow save the Moore's law. And the second part of it is, can we do something from the software system level, especially the performance engineering of software system to improve the performance? And here the performance is can referring to different parts, for example, the running time and the energy efficiency, and also the robustness of the code. And so sometimes we also do verification to ensure that the optimization you have done is correct. Okay, so that is something about my research, and I'm lucky to work with a series of great students, and they have achieved a lot of progress, and a lot of our works has already been incorporated into softwares in these large companies. And here in this talk, I will mainly focus on the two parts of our performance engineering of software systems, especially from the compiler and runtime. And these are the two major software stack we are aiming at to solve the problem. And here I want to give you a motivation about why we want to care about performance engineering, especially from the software perspective. And here, this figure just to tell you, even on the same machine, for example, from the Intel Xeon machine, which comes with 10 cores, and what is the performance difference when you use different kind of programming language and the different kind of optimizations. And you can see here, the running time and the G flops here, there could be even five magnitudes of difference in the G flops of different kind of implementations. And people in the industry are for application development, they use Python. The Python is great for development, but its performance is not as designed. And one of the key reasons is because Python is interpreted while like Java and C, this kind of languages, they are compiled. And compilation will give you a huge performance improvement. And later you will find that when we do other optimizations, like the loop optimization by exchanging the loops, we can have better data locality, and this will also lead to better performance. And parallelization loops is also important because, for example, for Intel, for NVIDIA, for CPU and GPUs, we can have a lot of cores, and by utilizing this cores will definitely give us a great performance. And also this kind of parallel divide and conquer will help us to utilize these several layers of cache on the hardware. And there are also some other levels of optimization. And from this figure, I just want to tell you that software optimization is very crucial, and it could give you a huge performance improvement. And even we are working on software optimizations, we need to care about the hardware. We need to know the hardware features so that we know how to develop our software. So software and hardware are always integrated. So even our optimization are at software level, we need to know a lot of details details about the hardware to match our application with the hardware. Okay, so that is our insights. Okay, so now we know like the software performance engineering is very important. So why we want to focus on the AI GPU acceleration? It's kind of a small topic under the big umbrella. So the first reason I think is AI is everywhere. It has been used in all different kind of application, in different kind of research topics, and it takes a huge amount of energies for both training and also inference. And why people want to investigate a lot of money into AI is because AI will bring us bring benefits to them from a company's perspective or even from nation's perspective. They are very important. And if you not only from the application perspective, but also AI has been driven the exploration of different kind of research topics from chemistry to physics to biology and even subtopics in computer science. So that's the reason we care about these AI applications. And then how about GPU? Why GPU? You can see a lot of my research is focusing on GPU. And one of the reasons is GPUs are one of the main workhorse for AI acceleration. However, the performance optimization on GPUs are not easy. If you look at the GPU, they have like, for example, this kind of NVIDIA A100 GPU have over 100 SMs and 6,000 CUDA cores and 400 tensor cores. To fully utilize all these cores in an efficient way and to utilize this kind of caches, short memories in a good way, it's not that easy. Okay, so it requires a great understanding of the hardware and also your application. Okay, yeah, and especially usually we have this kind of trade-offs between the parallelism, the memory optimization, and the data synchronization. And we have trade-off between computation, redundant computation, and also like the parallelism and dependency. So there's a lot of design choices there, and that's which is not in other words, there's no one solution to all problems. So it's kind of you have to tailor your optimizations to each of these applications. It's very tedious and it's very hard. Okay. And what is the worst part is the AI models are developing so fast, and we are not only having larger and larger models, meaning that we need to apply this optimization. Otherwise, we cannot run them in some day, right? And will be bottlenecked by the performance or bottlenecked by the capability of run these AI models. And from the other perspective, the AI models are become more diverse, seeing that they are not only previously like CNN or like convolutional neural network, they have convolutional operators and the matrix operations, but now we can have more diverse operations. So how can we automatically support all these kind of operations, all these kind of AI models in an efficient way becomes a very hot topic, okay, and requires a lot of optimization. And based on that introduction, I think comes to my view of the performance optimization for AI GPU in my group. In general speaking, I feel that manual optimization is not scalable and that will not be the solution we are looking for. So we have to work on some automatic solution. And I know that a lot of people, even myself, are working on a lot of hand-coded libraries. These libraries can do great works and can be applied to different kind of applications. But the problem is usually this kind of libraries lacks of adoption, and sometimes a good library is just missing because you are coming up with a new AI model. For example, like when quantized AI models were first brought up, GPUs, for example, this hardware, they do not really have the support for this kind of different kind of precision computations. Even though later NVIDIA come up with this kind of tensor cores, and it can support different kind of precision. It only supports, for example, 1 bit, 4 bit, 8 bit. But what if your workload finds that a 3-bit operation is the best? and it gives you good performance. So there's no library. How do you want to deal with it? Okay, so that is what I mean here by lack of adaptation, and sometimes it's just missing there. So my solution here, or my feel that is a great trend for solving this kind of problem is automatic and smart optimizations. And especially I emphasize on the compiler and runtime. So you may not even get this kind of keywords from my paper, the title of my paper, but you can get the sense from it. So what is a compiler in my mind? So compiler is something that help you to do the automatic transformation and with the optimization applied along the way. So that is my definition of the compiler. And usually in modern world, and what compiler is usually do is it come up with a set of composable templates, and these templates just encode the kind of optimizations that is tailored for the hardware. Okay, and then how to compose these templates together, and especially a lot of templates have some hyperparameters. So we will need to rely on the auto-tuning. Okay, and the auto-tuning will tell us like the right way to choose the hyperparameters in our templates, and also how to compose them efficiently to solve our problem. Okay, so that is a compiler in my mind. And one key question in this way, and has not been solved yet, is can we even automatically generate a template? Okay, and by predicting the future trend of the hardware involvement and a good prediction of the environment of the AI application development. Even we do not know the future hardware or future application, we know like how they will develop. What is the trend there? We can still like maybe automatically generate this kind of templates. That is a compiler's perspective. Compiler's optimization is usually static, meaning that when we compile a code, we will get optimized code, and this optimized code is rigid and it's there. So when do we need to have runtime optimization? Runtime optimization is usually complementary to the compiler optimization, saying that when we have an application and the best optimization is not known, because the optimization also depends on the inputs. So how can this happen? And one direct source is some of the GN applications, right? And the GN graph neural network, the performance really depends on the input graph. Okay, so how can you apply the optimization efficiently? Then we need runtime's help. Okay, and here is just one work in my group, and I just briefly discuss it. It's called like how we optimize GNNs on GPUs. And GNN is a special neural network. And one key thing here is it combines the traditional graph analytics and also the neural network. And traditional graph analytics has very irregular computation pattern and requires a lot of optimizations, while this neural network is more dense and regular. So it creates a significant optimization challenges here. And our optimization here is try to build an automated framework, as this framework will utilize the input features of the graph, and applies optimization dynamically. And also we have crafted this kind of kernels. If you think about it, it's a compiler's templates. And these templates just extract the most optimization opportunities from the hardware and the application. And by combining this kind of templates and runtime information, we could generate optimized code efficiently. And one benefit from this framework is this proposed optimization strategy has been simply integrated with existing framework, the PyTorch front end. Saying that the programmer still can use their favorite Python code, Python interface to do the programming, but automatically gain this kind of performance improvement. Okay. And here is just our evaluation. So we have evaluated a series of GN models, and we have covered a bunch of like data sets. And we also tested our framework on different types of GPUs. And the results is quite promising. And our framework can be both applied to inference and training. And we have times of speed ups. So I think this is the last slide of my talk, and just want to tell you that our group have done a lot of research regarding like AI GPU accelerations, and especially from the perspective how to from quantization sparsity, if they, from the application perspective, if we have this kind of features, how can we stitch this kind of input or like application features with the hardware, and also like our group also have some ML accelerator designs. Sometimes the application or the optimization just cannot be satisfied by the current hardware. So can we have specialized hardware to fully exploit the performance potential, and some part of the other part of my research is about the adversarial attack and defense, and that is a major concern when we apply application ML models. They give us great performance and accuracy, but sometimes it's just not that robust. So how can we do some optimization to defend the attacks? That is some other part of my research. Okay, so thank you. That's all for my talk. Thank you. Any questions here?
Thank you so much, Yufei. Yes, there is a question around C, Java, Python. They have different memory management models. How does the compiler optimizers take this into account?
So the question is about the memory models.
Yeah. See, Java, Python having different memory management models, and then how the compiler takes this into account.
Okay, so that is a very general question. For example, for Java, we think we have the garbage collection to efficiently utilize the memory, right? And for C, we do not really have that problem. But here, my topic is more about like compiler optimization for these AI models. So our templates will already extracted all this kind of memory model into we'll have this kind of memory model into consideration when we define our templates, and the key question is how to define this kind of templates and how to compose them together, and especially some templates there are some hyperparameters, and how to select the best set of hyperparameters according to your application and your hardware.
Okay, excellent. Thank you, Yufei. Clearly, this is going to be a key area in terms of getting to that aggressive targets that we have. So thank you for the presentation today.